All right, so let's get started. So a brief summary of what we discussed on Monday first. So we discussed essentially what solid-state physics is not. We discussed the macroscopic extreme, and so we try to identify where in the macroscopic world we can find evidences of properties that might actually be connected to the microscopic scale. But of course, we're not going to focus during our lectures on the macroscopic aspects. We're going to focus on the atomistic aspects, of course. And also, we briefly discussed at the end what solid-state physics is not on the other side, namely on small sizes and time scales. We discussed the fact that the nuclear physics is in principle not of interest to us, not because it is not relevant, but because the implications of nuclear physics are simple for us, and we can just take the results of nuclear physics and consider ions or nuclei as an entity without us having to know what are the details of what takes place inside the nucleus, for example. Okay, so we're going to concentrate on a few basic ingredients that we borrow from fundamental physics. One is quantum mechanics, the other one is electromagnetism. The basic particles will be the nuclei as a single entity, of course, for us, the electrons, and we'll be using quantum mechanics and classical mechanics to develop our understanding of the properties of solids and of materials. So let me now briefly, since I promised it last time, give you an outline of the course, of the topics that I hope we'll be able to cover during the course. So this is the outline of the course. So of course there was an introduction, which we already discussed yesterday, on Monday. But let me begin with the first real topic, which we're going to start today. And today we're going to discuss the lattices. And we're also going to discuss in more detail what crystals are. And we are going to develop a mathematical theory for that. Now, I understand that many of you might be already familiar with this concept, but it's good to fix the mathematics first, because these concepts are going to be useful extensively throughout our classes in the next lectures. We will also discuss later on the reciprocal lattice. Of course, this is done in connection with X-ray diffraction. In fact, the way we will discuss it is by discussing what X-ray diffraction is first, and then we'll see that X-ray diffraction can be easily understood if one introduces this mathematical concept of the reciprocal lattice, which of course is a consequence of the concept of a lattice and of a crystal structure. We will then start discussing more. We're going a bit deeper in the electronic properties of solids, and I will have to start with a bit of refreshing concepts in atomic physics. What kind of electrons are important for us. We'll probably also refresh some concepts of chemistry, the concept of valence electrons, for example. What are valence electrons? Because these are very important for us in our discussion. And then I'm going to discuss in some depth the concept of bonds, of chemical bonds. And here we're going to discuss different types of bonds, from the covalent bond to the ionic bond to the weaker bonds to hydrogen bonds. We're going to spend probably a couple of lectures on that. Of course, what one needs to keep in mind is that there is no real distinction between different types of bonds. It's just, a qualitative distinction. So we're going to take extreme cases to discuss properties and also mathematical tools and theories that allow us to understand the chemical bonds, but always keeping in mind that the real bond is something that is typically a combination of different effects and different phenomena causing atoms to like each other, to bind, to form bonds. And this is, of course, the basic subject that allows us to then extend our study to more complicated systems like solids, extended assemblages of atoms, not just pairs of atoms binding to each other. So after we discuss the chemical bonds, we're going to briefly discuss also the concept of binding energy. And connected to that, we're going to discuss vibrations. So once we understand how atoms bind together and they form the solids, it is very interesting to look at what happens if you perturb these solids, these fixed arrangements of atoms. And we're going to discuss, therefore, the phenomenon of vibrations, that is, small displacements out of the equilibrium position for the atoms. We're going to see it both in terms of vibrations in molecules, in finite systems, but also in terms of collective vibrations of an extended infinite system, in principle. After we are done with this, and this sort of ends the more mechanical part of the course, mechanical in the sense that we're looking at more mechanical structural properties of solids, we're going to start a discussion about the electronic states. So we're going to go back to point 3, and from here, essentially, we're going to restart the discussion about the ways electrons arrange themselves in solids. And so we're going to start with a discussion of a very interesting model. So now we're going to start the discussion of the electronic states. And in particular, the first example that we will make is the tight binding model. It's a very powerful model that allows us to understand a number of interesting properties of electronic states in solids. And together with that, actually, to the opposite side of the approximations, and we'll come back to these details later on, we're going to consider also the quasi-free electron model. So in one model, in the tight binding model, the assumption is that electrons are still tightly bound to the atoms. So atomic physics is a very good starting point to describe the electronic states in the tight binding model in a solid. Vice versa, the quasi-free electron model is a model where you assume that the starting point is free electrons, slightly perturbed by the presence of an underlying lattice of nuclei. So they're quite distinct in the way you handle the electronic states. And the results, of course, are also quite different. And of course, they apply to different solids. Some solids are better described by this approximation. Some other solids are better described by this approximation. Connected to that, and in fact, in parallel to this, I'm now referring to this as 8, but in fact, we are going to discuss it, in parallel with our discussion about the electronic states in tight binding and quasi-free electron model. I'd like to say something about more general properties of electronic states. So this is also electronic states, but more general properties. And these general properties are, well, first of all, it's Bloch's theorem. We're going to discuss it in conjunction with this, so it's not really a separate topic. It's something that we're going to discuss in parallel, going back and forth from the models to the general theory. Bloch's theorem, and of course the concept of Brillouin zone and finally band structure. This is probably one of the most powerful concepts in solid state theory. Mathematical theories that allow us to describe electronic states in a very powerful way, with a lot of consequences for what concerns the properties of solids. electronic properties, of course. And then we move on and discuss some consequences of applications of our theory of electronic states, and there will be a number of them. We're going to discuss a little bit transport, so how electrons move. Of course, I'm talking about electronic transport. And then we're going to discuss also briefly optical properties. They're all connected to the electronic states, of course. Once you know and you understand the details of these theories, then it's quite straightforward to extend them and to apply them to real properties like transport, conductivity, optical properties, and so on and so forth. Then at this point, the plan becomes a bit vaguer, and it really depends on where we stand towards the end of the course. There are a number of topics that we might be able to cover, but I'm not so sure, depending on really where we get by the end of the course. Some optional topics might include semiconductors, other possibilities to look at magnetism. We'll see later on. But I would say this is really the bulk of the course, and then we'll perhaps consider a few additional topics if time allows us. All right. So I'd like to start today with the discussion on lattices and crystals. Okay, so the first lecture is going to be on lattice. In fact, it's going to take us a bit more than one lecture, I guess. Okay. So first, we have to come back to a discussion we already made Monday. That is, we all know, although we're going to detail it a bit further today and also in the next lectures, we know that atoms like to arrange in a regular fashion, right? Well, we know it because there is experimental evidence for that, and we're going to come back to that in a couple of lectures when we will discuss X-ray diffraction. X-ray diffraction is a very powerful tool to realize and to extract evidence about the ordering of atoms in a solid. But I guess we are already familiar with this aspect, so I don't need to do X-ray diffraction first. Let's go directly to the evidence that we have that crystals exist. So there are atoms like to arrange themselves. Of course, this is supposed to be ordered. It's not just because I'm not very good at drawing things, but you should expect atoms to be arranged in a regular fashion, right? And as we discussed last time, of course, there is no such a thing as an infinite crystals. We like to think, and we will like to think in our theory that the crystals extend from minus to plus infinity, but of course we have to consider there are boundaries, there are grains, or even if there are no grains, at some point the crystal reaches a surface, so the surface breaks the translational symmetry, obviously. So we always have to keep in mind that when we discuss lattices, we are going to do it with a theory that assumes that the lattice is an infinite object, but of course we always have to keep in mind that there is no such a thing as an infinite object in nature. Real materials, real solids are always finite, whether because they are consisting of grains or because they're consisting of finite objects with surfaces where clearly the order terminates. Still, I mean, we would like to build a theory that is, say, nice to work with. So we're going to assume for a number of further theories that our lattices are composed of an infinite number of atoms. So we want to describe geometrically now an infinite array of atoms ordered in some fashion. And the way we're going to do it is by introducing a very important notion. And this is the notion of the Bravais lattice. Notice that I'm giving us a name, Bravais lattice. What is the Bravais lattice? The Bravais lattice is a geometrical concept. It's the set of all R's, all vectors are that can be written in this form. N1, A1 plus N2, A2 plus N3, A3, where N1, N2, and N3 are integers, positive and negative, of course, and A1, A2, and A3 are three independent vectors in 3 dimensions. Okay? A1, A2, and A3 are independent vectors. I assume that I'm working in 3 dimensions because that's the natural place where we do our theories, we build our theories. Independent means that they are not linearly dependent one with respect to the other, right? So I cannot write, say, A3 as a linear combination of A1 and A2, and A2 as a linear combination of A1 and A3. So there are 3 linear independent vectors in 3 dimensions. Okay? So this must be given. If I give you this, the Bravais lattice is identified by all points that satisfy this condition for all N1, N2, and N3 integers. Okay? All of them. All possible integers, N1, N2, and N3. These 3 vectors take the name of primitive vectors. Now, of course, there is an obvious generalization to different dimensions than 3, obviously, right? If I work in 2 dimensions, then what I have to do is simply to consider 2 independent vectors instead of 3, right? If I'm in 1 dimension, there's only 1 vector. If I'm in 4 dimensions, I have to introduce 4 independent vectors and so on and so forth, and of course 4 integers. But let's stick to 3 dimensions because this is where we really want to study our, systems, our real systems. In fact, because the blackboard is flat, let me for a time being consider 2 dimensions, just because it's easier for me to make drawings at the blackboard. So let me immediately show you an example now in 2 dimensions. So let's consider this arrangement of atoms, of points. In fact, I shouldn't call them atoms because this is now really a geometrical theory. I'm not saying that these are atoms. I'm just saying that these are vectors, right? So I'm talking about geometry here. I'm not really talking about. So they have points in space. And this array extends from plus to minus infinity. It covers the whole space, 2-dimensional space here. Now, yes? It's a definition, yeah. It's a definition. So the definition is, given 3 independent vectors, which I call primitive vectors, linear independent, a Bravais lattice is the set of all vectors, capital R, such that R is given by this expression for all possible values of N1, N2, and N3 integers. Okay? It's a definition. This is what I define as a Bravais lattice. Okay?
I thought, why they call Bravais?
Because there are different.
Is there a meaning behind the word?
Well, it's just an historical name. Bravais is a mathematician, and was a mathematician. Is the first one who introduced this concept. The reason why we call it Bravais and not just lattice is because there are different kinds of lattice that we're going to introduce later on. Okay, so this is some sort of primitive mathematical entity that we want to introduce to start our discussion. And we call it Bravais lattice, and that's the tradition. That's the way solid-state physicists call this mathematical object. All right? So now I'm going to visualize it now in 2 dimensions, unfortunately. So you have to now think of 2 independent vectors and all possible integers and blah, blah, blah. But I hope the discussion is clear anyway. So this is my array of ordered points. And if I say place the origin here, for example, then it is clear that if I consider A1 and A2 as these 2 vectors, I clearly generate the whole lattice using this definition. So what I'm visualizing here as clearly as an ordered array of points can be mathematically described by this definition, as long as I choose A1 and A2 as the two primitive lattices, as the two primitive vectors, sorry, two primitive vectors. Okay, so once A1 and A2 are given, this definition corresponds to the set of points that I have in mind that I want to describe here. For example, I mean, this point here will be characterized by n1 equals to 1 and n2 equals to 1, right? It's the point characterized by a1 plus a2. If I write it in this form. Now, we are forgetting about a3 because we are in 2 dimensions, right? Right. So this point here will be, well, let me write it. This is clearly a1 plus a2. So this corresponds to n1 equals to 1 and n2 equals to 2, obviously. What about this point here? n1 equals 1 and n2 equals 0. Okay, so this is 1, 0. What about this one? 2, 1, right? n1 equals to 2 and n2 equals to 1, and so on and so forth. If I go back here, this one, minus 1 and 1, obviously. Okay, I'm probably saying trivial things, but let's, start this building our mathematical tools before we move ahead to more complex things. Okay, so I can characterize every point, and I can assign to every point in this lattice, I can assign 2 numbers, 2 integers, and these integers are the ones that allow me to describe that point using this definition with a1 and a2 given. Now, let's try to understand a little bit better this definition. Suppose that now my system, instead of extending from minus infinity to plus infinity, was just limited to this piece of material. Okay, I have a piece of material made of whatever, 16 points, very ordered, regularly arranged in these points. Is this a Bravais lattice? Can this be described as a Bravais lattice or not?
With the proper boundary conditions?
I'm asking you the question, is this set of points, can this set of points be described by this definition? It's a mathematical statement. No. No, because here I'm saying for all n1, n2, and n3, right? So I cannot stop. If I whatever primitive choice of the primitive vectors I make, I need to include infinitely many points. I cannot stop myself somewhere. I have to consider infinitely many points. Okay? So a finite system is certainly not going to be described by a Bravais lattice. A finite system. It has to be infinitely big, obviously.
But if we use periodic boundary conditions?
We'll come back to that later on. Now we're discussing mathematics, okay? And that's the definition, and this is what we are trying to describe, okay? So with this, if this is what we're trying to describe, and this is the definition, the answer is no. This definition does not apply to a finite system, clearly. All right. Second question. Suppose I now have an infinite system, so let me remove now the boundaries and assume that I'm extending really from minus infinity to plus infinity with my array of points. Is, for a given array of points, is the choice of A1 and A2 unique? Certainly, if I give you A1 and A2, I uniquely identify what is the lattice, right? Because I just need to construct it. I give you A1 and A2, and I construct all the points that satisfy this condition. That generates a lattice by definition. But what about the opposite? Suppose I give you the lattice, for example, this one. Is the choice of the primitive vectors unique or not? Some of you argue that it's not, of course, and it is, of course, not true. In particular, for this one, take, now I need to, take A1 and A2. Question, does this choice, the green choice of A1 and A2, generate the same lattice that was generated by the pink ones or not? Yes or no? Yes, it does, right? For example, I can easily reach this point. Of course, in reaching this point, I have to do it by adding A1 and A2. So in my green notation, this is actually 1, 1. It's no longer 2, 1, right? And what about this one? How do I reach this point? Minus 1, 1, right? I first go along A2, and then I simply come back adding minus A1, right? Well, I'm not going to do it for all the points, of course, but it's clear that with this green choice of A1 and A2, I can generate exactly the same lattice. Do I generate more points than the pink choice? Is there any additional point that I'm generating with the green choice that I was not generating with the pink choice? No, right? For an obvious reason, because A2 is a linear combination of A1 plus A2. So as soon as I write this integer times A1, integer times A2, I'm writing also integer times A1, integer times the pink ones. Okay, so I'm generating the same points I was generating using the old definition with the pink vectors.
Please,
Yep.
if you want to construct, you are obliged to use the point or just to consider some property, geometrical property.
I'm discussing now points. For me, the space is empty. Is that your question?
No, I want to know because when you want to, the R is the resultant. R is like R.
Yes, R.
Okay, it's like the resultant of two vectors.
Yeah, so R is the resultant of the sum of two vectors, right?
When you take R1 and 2, just if you consider the parallelogram, you can construct without.
You want to consider this parallelogram, this one, for example? Okay.
So you can just consider this theorem for construct the resultant of the both vectors.
You mean this one is the resultant of the two vectors, of the A2 plus A1? Yes, this is what I use to write 1, 1. So what I'm saying is that this point can now be written as the sum of A2 and A1. Right?
Sure.
What was the question then? Okay, well. Okay, so the bottom line is the following. I have a lattice. The lattice can be, I mean, if it is a Bravais lattice, it must be described by this, by definition, by these conditions. However, there are infinitely many choices of the primitive vectors for a given Bravais lattice. Infinitely many, and you see it by considering, for example, this one. What about A2 and again, A1 being always the same? So A1 remains the same, but now A2 becomes this one. Is this a good choice of the primitive vectors for the same lattice? Yes, it is, because I can generate any point, for example, this one, by going upwards with A2 and then coming back with A1. In other words, I mean, from a geometrical point of view, I can move in this direction using A1 as many times as I want, and I can climb one floor by using A2. It doesn't matter whether I end up here, my stairs end up in a different place on this second floor, right? Because then I can move with A1. as much as I want. I mean, just need to add integers. So any A2 going from this point to any point along this infinite line is okay as a choice of the primitive vectors. It's going to generate exactly the same lattice. So in this particular case, at least, we've realized there are infinitely many choices of primitive vectors that generate the same Bravais lattice. All right? Yes?
This property also the one we introduce some impurities inside.
Oh, you're talking about impurities now. So you want to know whether these properties are retained when you introduce an impurity. Of course not. We're talking about an ideal system here. We're talking about the ideal system that not only does not contain impurities, but does not contain boundaries. It's infinitely extended. So it's clearly just a mathematical tool. No real system will ever be described by this, exactly by this. But it's a very good approximation. So if you want to study defects, for example, in impurities, you first do your theory for an ideal system, and then you see the consequences of perturbing your ideal system by introducing an impurity. Okay, so that's the strategy that we have in mind. We first want to be able to describe the ideal system, and then we'll take care of finite size, impurities, and all that. In fact, we're not going to discuss impurities during this course, but if you wanted to study impurities in solid-state physics, you would have to start from a theory of the ideal crystal and then see how an impurity perturbs the ideal crystal. Right? So here, of course, there are no impurities. If I introduce an impurity, that is, if I remove one of the atoms, say I remove this one, I just remove it, and I leave all the other atoms there, this is, of course, not a Bravais lattice any longer, okay? Because here I'm saying all integers. I'm not excluding anyone. If I remove this point, I would have to exclude the particular point with n1 equals to 2 and n2 equals to 0, right? While here I'm forced to include all of them. Okay, so an array of points where there is one missing atom, an impurity or a vacancy or something, is definitely not a Bravais lattice. Yeah.
When you contract your Bravais lattice, the origin is important for the beginning of
The origin is what? Is important? That's a good point. No, of course, because every property is invariant under translational symmetry. I mean, continuum translation. If I translate my whole solid by a finite amount, I'm clearly not going to change the physics, right? So let me decide to fix the origin at one of the Bravais points. In fact, I could choose to fix it here, and then I would still be describing the system in this way, but of course the origin of where I place my primitive vectors will be here and not here. But of course, this is trivial in some sense. I don't want to discuss this. I mean, the fact that I can place my primitive vectors here, or here, or here, or here, or here is somewhat, trivial. I'm not going to discuss it, let's say. Although, of course, it's a possibility. It depends where you place your origin. Allow me only to place the origin at the position of a Bravais point, or the Bravais lattice point, because that makes my life much simpler. Otherwise, I would have to add a constant vector here, of course. Okay. Now, examples of Bravais lattices in 2 dimensions. Well, this one is the so-called square lattice. The square lattice is characterized by, notice, a Bravais lattice is uniquely identified by the primitive vectors. If I give you the primitive vectors, that uniquely identifies the Bravais lattice. Not vice versa, of course. If I give a Bravais lattice, there may be infinite choices of the primitive vectors. But if I give you the primitive vectors, that uniquely identifies the Bravais lattice. Okay? So a square lattice is the lattice that is uniquely identified by 2 vectors A1 and A2, such that A1, the length of A1 is equal to the length of A2, and of course A1 and A2 are perpendicular. Okay, so this is what I define as square lattice, for example. Obviously, right? I think you're all fine with this I don't need really to explain too much about it. So I'm talking about examples of Bravais lattices in 2 dimensions now. What is another example of a lattice in 2 dimensions? An obvious extension of this one is the rectangular lattice. In this case, we have only that A1 is orthogonal to A2, period. The length of A1 and A2 can be anything. Okay, so what we are talking, so here we're talking about this particular lattice, the square lattice, and here we're talking about something that could be, for example, like this. Okay, and here, for example, the 2 primitive vectors could be A1 and A2. Right? And their length is not necessarily equal, while here it is equal. So this is called the square lattice, it is called the rectangular lattice. There's a very interesting example, another example of a 2-dimensional Bravais lattice in nature. It's actually very interesting for a number of reasons, and this is the so-called triangular lattice. It is interesting because it corresponds to the best way of packing circles in 2 dimensions. How do you pack circles in 2 dimensions? Well, if you put some circles here, you throw them on the floor, then of course the next ones will be sitting here, and the next ones will be sitting here. All right? So I'm trying now to pack spheres. Of course, I need to work with points. So what I mean by sphere, of course, identify. So these are the Bravais points, the Bravais lattice points. Now this is clearly neither a square lattice nor a rectangular lattice, obviously, right? If I can draw some lines here. Well, you see that they form triangles, right? It's a very natural lattice in 2 dimensions, this one. In fact, one may even argue that this is even more natural than the square lattice in some sense, because spheres, circles, are very symmetrical objects. So you place a very symmetrical objects, the most symmetrical objects you can think of, and you try to construct an array of very symmetrical objects, and the best way to pack them is by generating this triangular lattice. So in some sense, from a natural, definition, the triangular lattice is even more natural than the square lattice and any other lattice in 2 dimensions. So how can I describe a triangular lattice? Oh, first of all, is it a lattice? Is it a Bravais lattice? Can I describe it as a Bravais lattice? Is this a Bravais lattice? What I mean, of course, is the center of the circles. Are the center of the circles positioned in a Bravais lattice? Can I describe them with this Bravais lattice mathematical tool? Well, I need to identify the primitive vectors. Well, let me try with these 2 vectors, for example, this and this, A1 and A2. Okay? Am I generating the whole lattice with those 2 vectors? Well, yes, right? If I arrange all my points in these lines, I can clearly move along this line using A1 as many times as I want, and I can climb floors by using A2, right? So I clearly fill the whole, so all the points in my triangular lattice can be described by multiples, integers of A1 and A2. Am I missing any point? No. So I'm covering, so all the points that correspond to the centers of these circles can be obtained as a linear combination with integers of A1 and A2. And vice versa, if I build any possible linear combination of A1 and A2 with integers, I generate one of the points of the of the triangular lattice. So triangular lattice is characterized by primitive vectors which are equal in length and with an angle, let's say, let me write it like that, A1, A2, the angle equals to 60 degrees. So the angle between A1 and A2 is 60 degrees, this one here. This angle is 60 degrees, obviously, right? It's an equilateral triangle that I'm building there. Notice that after I give you this, you can forget about the way it has been constructed. You can be sure that if you have two vectors of equal length and they are at an angle of 60 degrees, one with respect to the other one, you construct a Bravais lattice starting from those two primitive vectors, you'll generate a triangular lattice, okay? Because this uniquely defines the lattice once the two vectors are given. So I need two vectors of equal length and with 60 degrees, one with respect to the other one. Then if I use those two vectors as the primitive vectors of my Bravais lattice in 2 dimensions, I generate a triangular lattice. Sometimes people like to call it hexagonal lattice, but it's, the simpler way to call it is the triangular lattice, actually. So I'll stick to this name, triangular lattice. Is there any other choice of the primitive vectors? Obviously, yes. We've just proven that there are infinitely many choices of the primitive vectors. I just wanted to show you another natural one. And this is A1 being the same, but A2 being this one. I like to mention this one because contrary to the square lattice, where there was a single natural choice, which is the one I've been using here, and then there were infinitely many other choices that clearly looked less natural than the best one, than this one. Here, there are actually two equally natural choices, the blue one and the green one. The only difference is that here I am 60 degrees and here I have 120 degrees. Okay, so I could equally say that the two angles could be 120 degrees and I would still be generating a triangular lattice. And it's equally natural. Okay? I certainly cannot say that, like in the square lattice, that there is one choice which is much more natural than the other ones, and this is this one, obviously. This one, the pink one. Clearly, the pink one is much more natural than the green one and the blue one. Here, I cannot say the same. Green and blue are the same as far as, so our symmetry ideas are concerned. Certainly, I can come up with more. I could choose A1 the same and A2 being, I don't know, this one, right? The vector going from here. Don't ask me to draw it because otherwise the plot is too messy. It would still be valid, but it would be less natural than the green and the blue one. Yes?
Is there any convention to choose the primitive?
No, the primitive vectors, no. With the only exception that there are systems for which one choice is more natural than the other ones. So you better choose that. Because, or for example, when the choice is not specified, it is typically the most natural one that you mean. In the case of the triangular lattice, in fact, there's a lot of ambiguity. Even if you read a paper, a research paper, they don't tell you sometimes whether it's 60 degrees or 120 degrees, so you have to be careful. Okay? While in all other cases, there is an obvious natural choice. Here, it's really a matter of taste. So there's no convention. My experience, after, say, 25 years of research, is that you find 120 degrees 60% of the times and 60 degrees 40% of the times. So, but this is really just... Okay. Yeah.
When we study Bravais lattice, are the constraints the same? Like
Are the what?
The Are we dealing the same kind of atoms or
The same kind of atoms?
inside the crystal the lattice?
We're not talking about atoms yet. We're talking about points.
Oh, just points.
They're points. We're not introducing, I mean, I'm using balls here, but just because I want you to keep in mind that sooner or later we will put atoms there. But so far I've only introduced a mathematical, geometrical concepts. So I'm not discussing atoms yet. But I mean, it's always a good thing to keep in mind that sooner or later we'll be replacing these points with atoms.
Yeah,
So
they
it's,
can be different, right?
they can be different. I'll come back to that in a few minutes. Yeah, in a few minutes, I guess. Yes. How do we define? How do we define a lattice? I haven't defined a lattice. So far, I've only defined a Bravais lattice. I'll come back to that later on. I haven't defined a lattice yet. What I've defined a Bravais lattice. Trust me, we'll get there at some point, okay? But I need to build the concepts one by one. So I've introduced this, which I call Bravais lattice, and this is the mathematical definition. Here are some examples. We've made some statements about the unicity of the primitive vectors, about the choice of the primitive vectors. That's it. I haven't defined yet what a lattice is, but we know what a Bravais lattice is, and I guess we know it in quite some detail by now. Okay. Let me give you another example of an ordered array of points. A nice one, by the way. I'm drawing lines here just to guide your eyes, but of course, the only geometrical entities that we've introduced are points. So I'm just introducing lines to guide you your eyes to this structure. This is the so-called honeycomb lattice. Okay, it's called honeycomb. Question. How can I express these points, this infinite set of points? Of course, I'm assuming here that I'm extending this from minus to plus infinity. How can I express it using my definition? If, of course, this is possible. This may not be necessarily possible.
We can choose a single point and then we can get three.
All right. Well, we are in 2 dimensions, so we only need 2 vectors, right? 2 primitive vectors. So let me start. Okay, let me put the origin here, for example. And according to what you're trying to say, let me try with A1 here and A2 here. Right? The simplest choice. I probably have another choice to put it here, but let's start with this one. Fine. Am I generating all the points of this lattice using A1 and A2 and integers? What about this one? Well, actually, what about something simpler? Wait a sec. What about this one here? It's slightly simpler. So I need to go from here up twice, right? And then come back once, right? Do we all agree? So this point is 1, 2 in our language. No? You don't agree with this? It is correct, right? I have to go up twice, and I will go here at the center, and then I come back here, and I get 1 and 2. What about this one? Well, this is more or less the same, right? I go twice, and then I come back. So this is going to be 2 and 1. And I can do it. What about this? Well, if this was 1 and 2, I simply need to add another A1, and I get there. So this is 2, 2. But wait a second, where is 1, 1? Where is it? It's here. But there's no point there. Hmm?
So it's not Bravais lattice.
It is not a Bravais lattice. Because once I give you the primitive vectors, all the points that can be obtained through integers must belong to the Bravais lattice. But wait a second, I might have missed something, right? I might have started with the wrong primitive vectors, right? I started with a given choice of primitive vectors and have been unable to generate the Bravais lattice. But perhaps there is another choice. Who knows? Is there another choice of the primitive vectors that allows me to construct this honeycomb lattice and therefore showing that this is a Bravais lattice? If it is, of course. Well, I have all the other choices, say, with this vector here, and I can try. But I mean, this system has clearly rotational symmetry, right? It's 120, rotated by 120 degrees, nothing changes. Now, let's think a little bit. Yes? What is the angle between these two vectors? This must be 120 degrees, obviously, right?
Because if it's not that, I don't think the coordinate of those points.
No, it is 120 degrees. Yeah. Still, I mean, I have to find primitive vectors that define that lattice. Can I find them? Okay, let me remark something. This vector here must be, if this is a, let me reason, I mean, if this is a Bravais lattice vector, and it must be, if I want this to be a Bravais lattice, this must be a Bravais lattice vector. I take twice that vector. If the original vector was a Bravais lattice vector, and I take twice that vector will also be made of integers, twice as big as the previous one. So any Bravais lattice vector that I take twice that vector must be a Bravais lattice vector, right? Because if I was able to write the first vector in terms of integer times my primitive vectors, whatever the primitive vectors are, I take twice that vector. I simply need to take twice an integer which is two integers which are twice the original integers, and I'm done. With integers, I can always find an integer which is twice the original integer. What I'm trying to say here is that an important property of a Bravais lattice is that if a Bravais lattice vector belongs to the lattice, obviously, then also any multiple of that vector must belong to the lattice. Now, if this vector belongs to the lattice, any multiple, including twice that vector, must belong to the lattice. And this is a general property. It doesn't depend on whether the lattice is square, rectangular, triangular, whatever. It's a general property of a Bravais lattice. It's an obvious consequence of the definition, of the mathematical definition. So therefore, the honeycomb lattice is not a Bravais lattice. Right? We've been unable to find the primitive vectors, okay, but this is not a good proof. This is not enough. The proof is that in a Bravais lattice, if a Bravais lattice vector belongs to the Bravais lattice, also twice that vector must belong to the Bravais lattice, which is clearly not the case for the honeycomb lattice. Because if this is a Bravais lattice vector, twice that vector brings me to something, to a place where there's nothing. Okay? So this is a mathematical proof that the honeycomb lattice cannot be a Bravais lattice. Okay, so that partially answers who was asking a question about you were asking a question about what is the lattice. Okay, so here we have a lattice that is not a Bravais lattice. So we clearly need to extend this definition if we want to include this lattice, certainly. Okay? This is not enough. This is not a good mathematical definition if we want to include, if we want to do it, of course, if we want to include this. But this exists in nature, right? I'm sure you've heard about graphene, right? This two-dimensional object. It's probably the only two-dimensional material that has never ever been synthesized in nature. So it's really the unique example of a two-dimensional system. And that two-dimensional system crystallizes in 2 dimensions into this honeycomb lattice. It's made of carbon, right? It's one single sheet of graphite. You exfoliate it and you get this beautiful two-dimensional system made of carbon atoms. And this is a honeycomb lattice. Unfortunately, this is not a Bravais lattice. So we need to do something. We need to play with our definitions in order to be able to include also these lattices. Was there a question? No, you were? No? Sorry, I missed. So how do we include, how do we extend the definition of a Bravais lattice in order to include also these lattices? We're now going to extend it. So we're now going to introduce the concept of crystal structure. It's another definition. Or, say it in a different way, lattice with a basis. What is a crystal structure or a lattice with a basis? I mean, you can take both. It's a definition, again, it's a mathematical definition. It's the set of all points R that can be obtained as N1, N1, A1 plus N2, A2 plus N3, A3 plus an arbitrary vector Bi, and I can do it with a set of vectors Bi's, I mean B1, B2, Bn. So, let me repeat it. In order to define a crystal structure or a lattice with a basis, I now need to introduce more vectors. I need to introduce my primitive vectors. So I need to tell you what the primitive vectors are, and there are 3 in 3 dimensions, 2 in 2 dimensions. But in addition to that, I have to give you also another set of vectors, which is called the basis. So this is called the basis. It's a set of n, where n is finite, vectors that I need to provide you. Okay? So in order to define a crystal structure, a lattice with a basis, I need to provide you with 3 in 3 dimensions independent vectors, plus I need to provide you with a set of n vectors, which I call the basis. After I've done this, we define the crystal structure, or the lattice with a basis, the set of all vectors which can be expressed in this form with n1, n2, and n3 all possible integers, and bi any possible value of the basis vectors, any possible element of the basis vectors. Okay? Let me give you an example before we get lost. So now the definition requires more than 3 vectors. It requires 3 plus n vectors in order for me to be able to identify uniquely the lattice with the basis, or the crystal structure. Okay, so let me do it now again in 2 dimensions. And let me start with the square lattice because it's simpler. Let me take a very simple example to start with. Okay, so I'm giving you A1. I'm giving you A2. These are equal and orthogonal, so this is a square lattice. So I'm generating all the points in infinite points that are identified by that. But then I also give you n vectors. Let me fix n equals to 2 for simplicity. Okay, but it can be more than that, of course. And it can be something like, this is B1, and, well, this is B2, for example. I made B1 and B2 smaller than A1 and A2, but there's no reason why they should be smaller than that. Anyway, just for the sake of visualization, I'm choosing that B1 and B2 are smaller than A1 and A2 in length. Now, what do I mean by now the crystal structure constructed from A1 and A2 as primitive vectors and B1 and B2 as vectors in the basis? I mean all the points that can be generated in this form. That is, all points, I first have to identify all the Bravais lattice points generated by A1 and A2. And after that, I have to add either B1 or B2. So if I consider 0, 0, which is the origin here, the 2 points will be this and this. So these 2 points will belong to my crystal structure. Let me now take another Bravais lattice point, this one. I have to consider all the points that belong to the Bravais lattice plus B1 and B2 again. So I have to go here and here. Let me consider this point. This is also a Bravais lattice point. I have to add B1 and B2. And these are my 2 points. I'm using shades to identify those points. And so on and so forth. Okay? So all these green points will belong to this crystal structure. Notice that unless one of the B's is the 0 vector, unless it is a 0 vector, the Bravais lattice points do not belong to the crystal structure. Right? Because I need to add the bases here. I need to add all of them. And if none of them is 0, I will never touch a Bravais lattice point because I will have to first move to the Bravais lattice point and then add any of these vectors. But if these vectors are not 0, I will have to move away from that point. Okay? So the green shadows here are the points that I'm generating according to my definition of A1 and A2 as the primitive vectors and B1 and B2 as the bases. I could, of course, have chosen more points in the basis, 3, 4, 5. I would have generated more points around here, and of course, more points around here as well, more points around here as well, more points around there as well. So I'm extending the definition of a lattice to arrays which are a bit more complex than the ones I was describing with the Bravais lattice concept. Right? Because the Bravais lattice only allowed me to describe simple lattices. The honeycomb lattice, for example, was not included in this definition. I could not describe the honeycomb lattice using the Bravais lattice. I'll show you in a second that you actually can describe the honeycomb lattice using this definition. So, in short, the crystal structure, or the lattice with the basis, is a Bravais lattice to which I'm adding more points for each Bravais lattice point. So I have to first generate my Bravais lattice, and then around my Bravais lattice point, I place my points in the same way around every Bravais lattice point in my lattice. Okay? But that gives me more freedom because it allows me to generate structures which are more complex than this one. By the way, it is clear that the Bravais lattice itself is a particular case of a crystal structure, right? I just need to choose n equals to 1 and b1 equals to 0, right? So the Bravais lattice is a particular case of a crystal structure. On the other hand, I need to introduce the Bravais lattice in order to introduce a crystal structure, because I need to know what this is before I can add the extra points around the Bravais lattice point. So the concept of a Bravais lattice is very important in the definition of a crystal structure. Even though, as I just said, the points that I'm generating with the crystal structures may not actually lie in Bravais lattice points. Yes?
Is the choice of primitive vectors?
Sorry?
Is the choice of primitive vectors still infinite?
Yes, because when I generate this, I can generate it in infinitely many ways, right? And I'm generating the same set of points, but just choosing two different choices of the primitive vectors. So that remains true. Okay? You have to think a crystal structure as a Bravais lattice with additional points around every point. How I generate the Bravais lattice, it's another story, and I can apply all my considerations that I've already applied to the Bravais lattice, including the fact that the choice is not unique of the primitive vectors. Now, going back to the translation question, obviously, I mean, in this case, I may wish to place the origin at one of the points. Instead of placing the origin here, I may wish to place the origin at, say, one of the points, for example. That might be more convenient in some cases. In that case, the only thing that changes if I change the origin is the definition of the basis vectors, right? Because if I place my origin here, for example, clearly b1 will be 0 and b2 will be this vector here. It's just a matter of, one has to be careful in the choice of basis vectors because there may be, you might find it more convenient to place the origin at the position of a point rather than to place it somewhere else and having to displace every time to reach your point from the Bravais lattice point. Okay? All right. Okay, so let me now go back to our honeycomb lattice and see how we can describe it with a lattice with the basis. I'm drawing a line again just to guide your eyes. All right, so where do we start? Well, we need to give the primitive vectors now. Well, let me guide you now. So a good choice of the primitive vectors is A1 and A2, for example. Now, this is going to give me all these points, right? Up, here. and this one, of course. But it's not going to give me these points, right? There's no way I can reach these small dots by building linear combinations with integers of A1 and A2. But I can decide that this point is B1 equals to 0, and this vector here is B2, right? So let me mark it with green here. Now, obviously, this point will be A1 plus B2. Same with this. Same with this. This one will be A2 minus A1, and I get here, and then I add B2. Okay? Every one of these small points can be reached from this Bravais lattice point by adding B2. Okay, so I'm now showing with green these points. All of them can be reached from the Bravais lattice point by adding B2. So in this particular case, I have the Bravais lattice is the triangular lattice generated by A1 and A2. And the basis is composed of two vectors. B1 is just 0. I just stay there. And B2 is this vector here. Okay? So if I give you these two primitive vectors and these two elements in the basis, you can tell me, well, this is the honeycomb lattice. I've been able to generate the honeycomb lattice. But unfortunately, I needed to introduce a basis. I was unable to describe the honeycomb lattice using a bare Bravais lattice. I need the Bravais lattice plus I need extra points inside for every Bravais lattice point in order to be able to introduce. Now that we, let's try and think at now filling these points with atoms, right? We have to remember that eventually we will consider this not just as a mathematical tool, a geometrical tool, but as a way to describe the position of the atoms in our crystal. And obviously, if you have a solid, the solid is not necessarily composed of atoms of the same kind. That may be carbon, nitrogen, oxygen, aluminum. I mean, it can be a complex material. And there are crystals which are composed of complex arrangements of elements, of different elements. Now, obviously, if you're dealing with a system, with a material, with a solid, with a crystal, which is composed of different elements, there is no way you can describe it using a Bravais lattice, because all the points would be equivalent, while you know that different points might correspond to different atoms. So you don't want to describe them as the same point. So the concept of a crystal structure or a lattice with a basis is particularly natural whenever you are dealing with materials which are not just made of a single element. If you have more than one element, you clearly need to distinguish atom white and atom green, right? So you need to have a basis of at least two vectors if you have two elements. If you have three elements, at least three vectors, right? If not more. Now, typical crystal structures, natural ones, they are described by, of course, a Bravais lattice, plus a basis, which is typically made of 1, 2, well, if it's 1, it is a Bravais lattice, but 2, 3, up to hundreds or thousands of atoms, okay, in the basis. So there's no limit in principle. The only limit is our ability to measure it, to detect it, that crystal structure. In fact, even though, in material science, in solid-state physics, crystal structures that we work with are typically made of at most 20, 30, 40 atoms, 40 elements in the basis. there are fields in which the number of vectors in the basis can be 100,000. This is the field of biochemistry. Probably the only way in which you can determine the structure of complex molecules like proteins, for example, is by crystallizing them. So you take proteins, all of the same kind, and then in some way you crystallize them. So you pack them together in such a way that they form an ordered array of complex molecules. And they are all the same. They just repeat themselves in an ordered way. Now, these are very complex crystals because the Bravais lattice can be anything. It can be, any Bravais lattice. But the number of points in the basis is huge because it's the number of atoms in your protein. Because each protein itself is repeating regularly. And each protein can have 100,000, a million atoms in the structure, right? So there are cases in which the Bravais lattice is something, and the basis is made of 1 million atoms, 1 million points. It's huge. Okay, so you have out of every Bravais lattice point, you have 1 million points around it, which correspond to the positions of the molecule. You have a complex molecule. Well, I shouldn't use the honeycomb lattice. Let me use the square one. So around each point, there is a very complex molecule. And that very complex molecule repeats itself regularly like this. But each one of these molecules can have up to 10 hundreds or million atoms. Okay? So the number of basis vectors, that is all the vectors that connect all the points all the atoms in the molecule, can be huge. This is not, fortunately, our problem. It's the problem of those who do biochemistry, who crystallize these macromolecules. In solid-state physics, you tend to work with a small number of points within every Bravais lattice point. But I just wanted to give you a flavor of what people do in fields that are not necessarily solid-state physics. And we'll come back to that when we discuss X-ray diffraction in a couple of lectures. All right. Let me spend the remaining 10 minutes going to 3 dimensions. We've been discussing so far only 2-dimensional lattices. Let me start moving to 3 dimensions. And let me start with Bravais lattices first. Okay, so I'm now going to give you a few trivial examples of Bravais lattices in 3 dimensions. In 3D. So the simplest one is the cubic lattice. The cubic lattice is defined by 3 generating vectors. And of course, I have to continue like this. But if I define the 3 vectors A1, A2, and A3, I'm clearly generating a cubic arrangement of atoms, right? So I'm generating all the points. Yes, coming. And so on and so forth, right? Yes?
Do we have other classes like Bravais lattice and crystal structure? I mean, like,
Do we have anything more than that? Well, then you start moving into the field of quasi-crystals, for example, which is a completely different and very complex topic. But as far as, say, standard solid-state physics is concerned, from the mathematical description of crystals ends with these 2 definitions. Okay?
are they good, really, those definitions?
With the exception of quasi-crystals, this is okay for everything. Okay? As long as it is periodic, of course. There is translational periodicity. Of course, you're not going to be able to describe glasses or amorphous systems with these mathematical tools. So that's a completely different story.
So if the object has some kind of symmetry, then
If there is translational order, right, then it can be described with these two, or in fact only with this one, since we've realized that the Bravais lattice is a particular case of a crystal structure. All right, so the Bravais lattice, so this is a very simple example, probably the simplest example. It's called the cubic lattice. Right here, A1 is equal to A2. Oh, now I have to introduce A3, of course, right? Because we are in 3 dimensions. And the 3 of them are perpendicular. Well, AI ij is equal to 0 if I is different from j. Okay? Equal length and perpendicular to one another. There are then other types of lattices, like you can have a lattice in which the base is still square, so A1 and A2 form a square lattice, but the 3rd dimension is arbitrary, perpendicular but arbitrary. Okay? So here I have A1 equals to A2, and then AI scalar AJ equals to 0 if. Okay? Not A3 can be anything of any length. Orthogonal to A1 and A2, but of any length. Okay? So this is called tetragonal lattice. These are examples of Bravais lattices in 3 dimensions. Okay? If I relax even this condition, but I keep the 3 vectors orthogonal, well, don't ask me to draw it now. If I just keep this condition, right, without saying anything about the length of A1 and A2 and A3, then this is called orthorhombic. Cubic, tetragonal, orthorhombic. Let me now start relaxing the condition that the primitive vectors need to be orthogonal. Let me consider a very interesting system, which is very interesting lattice, which is the one in which you have a triangular lattice in 2 dimensions, and then you add a 3rd dimension vertically. So you have A1 and you have A1 and A2. Now I'm using a projection now, right? I'm projecting it. And then A3 vertical. And these A1 and A2, they generate a triangular lattice, okay, in 2 dimensions. Okay, so A1 and A2 are a triangular lattice, which means A2 and A1 have the same length, and the angle is 60 degrees or 120 degrees. And then I have a 3rd vector, which is orthogonal to both. So A3 scalar A1 or A2 is 0. This is called the hexagonal lattice. In fact, that's the reason why some people call hexagonal a triangular one. I prefer to keep the correct definition, which is triangular for the 2-dimensional one, and hexagonal as soon as you add the 3rd direction as 3rd dimension. And then, I mean, this monoclinic, blah, 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 triclinic. When there is no relationship between A1, A2, and A3, they're just arbitrary vectors, you call them triclinic. There are a couple of other examples, but I really don't want to go into the details of that. Triclinic lattice, where no constraint. There's no constraint on A1, A2, and A3. It can be anything. There are two more cases, like the monoclinic and the rhombohedral, but I mean, it's just a matter of it's zoology. It's not really relevant. Although, of course, if you do research and you open a paper and they will tell you, this crystal is tetragonal, and they give you 2 numbers. In principle, if I want to identify a Bravais lattice, I need 3 vectors, right? So I need 9 numbers. So why do they give me just 2 numbers? Well, they give me 2 numbers because for a tetragonal lattice, the only thing I need to know is the length of A1 and the length of A3, right? I don't need to know anything else. If I tell you it's tetragonal, as long as we agree that the first number is the length of the base and the third number is the length of the third direction, I'm done. I just need to give you 2 numbers. Cubic lattice, I only need to give you 1 number, the length of this vector. I don't need to give you the nine numbers which identify the 3 vectors. On the contrary, for the hexagonal lattice, I also need to give you only 2 numbers, the length of this and the height of A3. And of course, I need to tell you it's hexagonal, so then you will know that you have to construct your primitive vectors 60 degrees or 120 degrees. Triclinic lattice, well, you have to give me everything. In fact, you don't really need to give me 9 numbers if you think about it, right? Because I can rotate my 3 vectors arbitrarily in space, and I will obtain the same system. So what defines the 3 vectors is not really their arbitrary position in space, but it's only their length, okay, 3 numbers, and the 3 vectors formed by the 3 pairs of primitive vectors. Okay, so it's a total of 6 numbers, 3 lengths and 3 angles. Once you have given me this, I can orient it the way I want, and I will generate exactly the same lattice. Of course, with a different orientation in space, but who cares about that, right? So that's important. If you open a paper and you'll find that the structure that they're dealing with is a triclinic structure, they will give you the 3 lengths, A, B, and C typically, and the 3 vectors between the 3 angles, between the 3 pairs of primitive vectors. Okay, so 6 numbers are enough to define the most general lattice, Bravais lattice, in 3 dimensions. Okay. Yes, this is a good point where to stop. Is there any question at this point? No? Okay, so I'll see you on Friday.